Hey everybody, today we're going to be talking about topic 1.2, mass spectrometry of the elements. Before we get into mass spectrometry in general, first I want to just give a brief review about the atom and some of the properties of the atom that we remember from our intro chemistry class. If I remember the atom, if we draw a very crude depiction of it, we have a nucleus that's positively charged in the center and a cloud of electrons around it that are negatively charged. The atom itself is about 1 to 5 angstrom in diameter, and 1 angstrom, if you're unfamiliar with this unit, is equal to 1 times 10 to the minus 10 meters. We have this electron cloud here, where all the electrons are whizzing around in different orbitals, and we'll be talking about orbitals later on in this course as well. Also in the nucleus, we have these other particles known as neutrons that don't really have a charge, but also stick into the middle right there. And so we draw a little bit of a chart of our particle, its charge, its location, right? Protons, those carry a charge of +1, and their location is in the nucleus. We can also look at the mass of each particle, and for protons, they weigh 1 AMU, or atomic mass unit. Now looking at neutrons, those carry no charge, so its charge is 0, also present in the nucleus, and its mass is also 1 AMU, so it contributes to the mass of the entire particle. Then we have the electrons. They carry a charge of -1. They're located around the nucleus in the electron cloud, and these are basically 0. Their mass is so small compared to protons and neutrons that we typically don't consider them within the mass calculation of a particle. Now, the mass of any atom can be determined by adding together the number of protons with the number of neutrons, and that will get you the overall mass of the atom. Now, if you want to look at the charge of an atom, that would be the number of protons minus the number of electrons, where if this number is greater than 0, you have a positive charge, but if it's less than 0, you have a negative charge. Now, elements also have what are known as isotopes. And so isotopes are forms of an element that have different masses. What do I mean by that? Let's take carbon, for example. Carbon has 6 protons in its nucleus, as well as 6 neutrons, for a total mass of 12 AMU. But carbon can also have, and this is carbon 13, 6 protons in its nucleus and 7 neutrons, for a total mass of 13 AMU. Now the charge, right? The charge is still the same. It's 0. If you have 6 electrons, 6 protons, and 6 neutrons, the charge is 0. If you have 6 protons, 6 electrons, and 7 neutrons, the charge is still 0. The only difference here is the mass of the carbon. Now here is just a table of some isotopes of carbon. You can have carbon 11, which will have 6 protons, 6 electrons, and 5 neutrons, making it its total mass 11. Carbon-12, which has 6 protons, 6 electrons, and 6 neutrons, is the most common form of carbon that we know of, and it's the most abundant, and that has a mass of 12. And then 13, we have 7 neutrons, and carbon-14 will have 8 neutrons. Now, all of this becomes important when we start thinking about mass spectrometry. Mass spectrometry is a technique that's typically used by chemists in the lab in order to determine what the mass of a particular sample or chemical compound that they're interested in weighs. And so you guys don't need to necessarily know all of the constituent or component parts of a mass spectrometer, but I wanted to take a second to just talk about it. So typically what you'll do is you'll add your sample right here at the start of the tube. It'll enter this chamber, and what will happen is it will ionize right here. Right? And so what will happen is an electron essentially gets ripped off of the molecule. What it'll do is it'll then accelerate through this little tube. There's a magnet here that will push it in this direction. And then what will happen is based on its mass, depending on its isotope, it will separate. And so this example here, you can see we have chlorine-35 and chlorine-37. Both of those will travel differently through that magnet as well as this detector. And the way it basically works is heavy. Oh, sorry, this pen is not working. Heavy isotopes travel a very, very short distance, but light isotopes travel very far. And so that difference in distances is what essentially gets us our differences in the mass spectrometer, which we'll see in an example in a few slides. Now, another important thing to remember is that with atomic weight, the way we calculate the atomic weight that we see on the periodic table, or when we're just looking at average atomic weights, is it's a weighted average. A weighted average is similar to the averages that you might have in a class, but it is the sum of the isotope's mass, right? So for carbon, that might be, right, 12 or 13, multiplied by the relative abundance divided by 100. And so you'll see this in an example in this slide right here, where we're looking at the atomic masses and abundance of iron. And so you can see we have different isotopes of iron right here on the left, iron 54, 56, 57, and 58. And we have a bunch of different abundances of those isotopes of iron as well. And so if we want to calculate the average atomic mass of iron, what we would do is for the average, that would be equal to the atomic mass, 53.9396 of iron 54, multiply that by the abundance in decimal form, so 0.05845, and then we would add that to the next isotope. So in that case, the atomic mass is 55.9349 times the abundance, 0.91754. Remembering again that we're always using the decimal form, not the percentage. Add that to 56.9354 times 2. Oh, my apologies. I almost just made the mistake I told y'all not to do. By the decimal form, 0.02119. And then finally, iron 58, which its atomic mass is 57.9333 times 0.00282. And that will give us our average atomic mass, which if we look at the periodic table for iron is 55.845 atomic mass units. And so if you were wondering how those average atomic masses appear on the periodic table, this is the calculation that gets us those masses. And so if you're ever asked for the average atomic masses, you can calculate them using the percent abundance multiplied by the atomic mass of that particular isotope. On the AP exam, and as well as exams and classes, you might get something like a mass spectrum like this. as I was saying earlier, you'll have different peaks in the mass spectrum corresponding to each of your different to each of your different isotopes. And so for the case of chlorine 35 and chlorine 37, you'll have two separate peaks. And it will give it to you as atomic mass versus the signal intensity. And so if you get a graph like this, you might be asked to compare the heights of these two, right? The height of chlorine 35 versus the height of chlorine 37, and tell them something about what the relative abundance of each is. And because the signal intensity is correlated to that percent abundance, taller peaks will be higher abundance, whereas shorter peaks will be lower abundance. And you can use these mass spectrum diagrams here to estimate the percent abundance of two different isotopes in a sample. Now, finally, I did want to take a little bit of time to look at this practice problem here at just kind of looking at this sample mass spectrum here. So let's take the time to answer a few of these questions. First, how many isotopes are there? Well, if we count every single one of these peaks right here, we can see there's 1, 2, 3, 4, and this tiny little peak at 96 is our fifth peak. And so we should have 5 isotopes in this mass spectrum. How do we know? Well, the number of peaks in the mass spectrum is equal to the number of isotopes, and so we just count the peaks. Simple enough. What do the relative height of lines give you? I just said in the previous slide, the height of lines will give you that relative abundance in relation to the other ones. And so the heights will give you relative abundance. What is the average atomic mass? That we can pretty easily calculate using our weighted average equation. So average is equal to, if we start with 90 times 0.51, not 0.051, plus 91 times 0.112, plus 92 times 0.171, plus 94 times 0.174, plus 96 times 0.028. And that is equal to 91.32 AMU. And again, if we look at our significant figures here, our masses are only 2 significant digits, and so this would actually be equal to 91 AMU if you round down. And if you look at the periodic table to see which element is represented, if you compare 91.32 AMU with the atomic masses given on the periodic table, you can see that this is zirconium, or ZR. We'll have a little bit more time to practice with this in class. Otherwise, I will see you then. Thank you.